Today we'll discuss a topic on photovoltaic solar power plant. Introduction. There is a pressing need to accelerate the development of advanced clean energy technologies in order to address the global challenges of energy security, climate and sustainable development. Photovoltaic cell, solar photovoltaic is a key technology option to realize the shift to a decarbonized energy supply and is projected to emerge as an attractive alternative electricity source in the future. India is located in the equatorial sun belt of the earth, thereby receiving abundant radiant energy from the sun. In most parts of India, clean sun weather is experienced 250 to 300 days, that is almost 300 days in a year. The highest annual global radiation is received in Rajasthan and northern Gujarat. In Rajasthan, large areas of land are barren and sparsely populated, making these areas suitable as locations for large central power stations based on solar energy. Indian government has launched Jawaharlal Nehru National Solar Mission JNNSM with a target of achieving 20,000 megawatt by 2022. The goal is to make India one of the leaders in solar energy. Although solar energy is still expensive today, but costs are coming down with technology development, right government policies and R&D efforts. Now let us see the technology for solar power plant. Solar power plant generation technologies can be broadly classified into two broad categories: solar photovoltaic technologies and other one is solar thermal power plants. Now let us see what is SPV technology, solar photovoltaic technology. Photovoltaic converters are semiconductor devices that convert part of the incident solar radiation directly into electrical energy. The most common PV cells are made from single crystal silicon, but there are many variations in cell material, design and methods of manufacture. The above technologies are mainly used on rooftops of commercial and residential buildings and as large scale grid connected power plants. For optimum output, larger installations are using tracking devices which change the orientation of panels to correspond with the trajectory of the sun to focus sunlight directly onto the panels. Now what is solar thermal power plants? Solar thermal power plants produce electricity by converting the solar radiation into high temperature heat using mirrors and reflectors. The collectors are referred to as solar field. This energy is used to heat a working fluid and produce steam. Steam is then used to rotate a turbine or power of an engine to drive a generator and produce electricity. Now let us see the major components of a solar photovoltaic power plant. The major components of a SPV power plants are modules, inverter, string monitor box, step-up transformer, AC DC cables, HT breaker, HT cable, SCADA and net metering. This is the block diagram of a solar power plant. On the left hand side modules are shown in arrays which is connected to string monitoring boxes, string using DC cables. These cables are connected to an inverter which converts DC into AC. 440 voltage is generated at the output of the inverter. It is connected to a step-up transformers. 400 volt AC is stepped up to 11 kV, 11,000 volt, which is connected to breakers. This power is taken to the main receiving station through HT cable and it is either exported or imported through net metering system. Now let us see the performance evaluation of a solar power plant. For complete performance evaluation, the following data has to be collected and verified to the extent possible. Number one is irradiation. As mentioned, data from different sources has been analyzed and the source identified based on the accuracy perception for the present study. Next is performance ratio. It is observed that performance ratio depends on the irradiation, the optimum angle of tilt, air temperature, design parameters, quality of modules and efficiency of inverter. Third one is degradation. All manufacturers stand a guarantee of performance over a period of 25 years with 90% output for first 12 years and up to 80% after 25 years of operation. Various studies carried out by global renowned institutions on the extent of degradation of output of modules after long term of operation in the field. These results are analyzed to arrive at the actual field performance. Next is life expectancy. Trends in the accelerated test for modules, inverters, supporting structure and cabling have been studied. Now let us say the performance of solar power plants. The performance of solar power plants is best identified by CUF, that is capacity utilization factor, which is the ratio of actual deficiency output from the plant to the maximum possible output during the year. The estimated output from the solar power plant depends on the design parameters and can be calculated using standard softwares. But since these are several variables which contribute to the final output from a plant, the CUF varies over a wide range. It is essential, therefore, to list the various factors that contribute to the plant output variation. The performance of the power plant, however, depends on several parameters, including the site location, solar insolation levels, climatic conditions, especially temperature, technical losses in cabling, module mismatch, soiling losses, MPPT losses, transformer losses and the inverter losses. Let us see what is MPPT losses. The power output of a solar PV module changes with change in direction of sun, changes in solar insolation level with varying temperature, etc. The PV, that is power versus voltage curve of the module, there is a single maximum of power, that is there exists a peak power corresponding to a particular voltage and current. Since the module efficiency is low, it is desirable to operate the module as the peak power point so that maximum power can be delivered to the load under varying temperatures and insolation condition. Hence, maximization of power improves the utilization of solar PV module. A maximum power point tracker, that is MPPT, is used for extracting the maximum power from the solar PV module and transferring that power to the load. MPPT, maximum power point tracking, is used to ensure that the panel output is always achieved at the maximum power point. Using MPPT significantly increases the output from the solar power plant. Now let us see the inverter efficiency. A solar PV inverter is a type of electrical inverter that is made to change the DC, direct current electricity, from a photovoltaic array into AC, alternating current, for use with home appliances or to be fed into a utility grid. These inverters may be standalone inverters which are used in isolated systems or grid tie inverters which are used to connect the power plant to the grid. Efficiency of inverter has to do with how well it converts the DC voltage into AC. The currently available grid connected inverters have efficiencies up to 96 to 98%, and hence choosing the correct inverter is crucial to the design of process. Now let us see the solar power plant design. Some critical factors which must be kept in mind during design include proper selection of modules, optimum angle of tilt, minimization of ohmic losses with proper selection of conductors, selection of efficient transformers and inverters, etc. Use of reliable and long life components is equally essential for expensive solar power plants. The actual energy output that can expect from a given PV system depends upon a large number of factors, and some of these are: the PV efficiency is affected to a greater or lesser extent by the temperature of module, usually decreasing with increasing temperature. Nearly all module types show decreasing efficiency with low light intensity. The strength of this effect varies between module types. Some of the light is reflected from the surface of the module and never reaches the actual PV material. How much depends on the angle at which the light strikes the module. The more the light comes from the side, the higher the percentage of reflected light. This effect varies between the module types. The conversion efficiency depends on the spectrum of solar radiation. Where nearly all PV technologies have good performance for visible light, there are large differences in the efficiency for near infrared radiation. If the spectrum of the lights were always the same in this effect, would be assumed to be part of normal efficiency of the modules. But the spectrum changes with the time of day and year and with the amount of diffuse light. Mounting position. For fixed systems, the way the modules are mounted will have an influence on the temperature of the module, which in turn affects the efficiency. Experiments have shown that if the movement of air behind the module is restricted, the modules can get considerable hotter, that is up to 15 degrees centigrade at 1000 watt per meter square of sunlight. Inclination angle. This is the angle of PV modules from the horizontal plane for a fixed mounting system. It is also noted that global radiation measurements are done on the horizontal surface. The maximum reduction can be obtained by tilting the surface at an optimum angle, which is determined by the latitude of the location. Module degradation. The degradation of solar modules with temperature and the time contributes significantly to the final output from the panel. The effect of degradation of photovoltaic solar modules and array and their subsequent loss of performance has a serious impact on the total energy generation. And with the respect to this maximum power at standard test condition, most manufacturers indicate the extent to which panels will degrade through the guarantee. This is specified as a ratio of the maximum power available at the time of installation. Most manufacturers claim their panels will produce 90% of the maximum power after a period of 10 years and 80% of the maximum power after 25 years. Hence, most power plants are also designed for a life of 25 years. Now, conclusions and recommendations. Solar, photovoltaic and thermal power plants will play an important role in the overall energy supply. The performance, CUF, capacity utilization factor, depends on several factors including the solar radiation, temperature, air velocity, apart from the module type and quality, angle of tilt, design parameters to avoid cable losses, and efficiencies of inverters and transformers. There are some inherent losses which can be reduced through proper designing but cannot be completely avoided. The modules show degradation in power output through years of operation. It is observed that quality modules is very important in determining the extent of degradation. The improvements in technology and quality assurance have reduced this degradation considerably. Jai Hind.